When you move to a new city, at first, you have a hard time navigating around even just your neighborhood. Safely getting to a new destination requires constant checking of Google Maps or asking strangers for directions. But as you walk around and awkwardly get lost every once in a while, your brain is constantly learning, and just in a few weeks, you'll find yourself taking shortcuts and casually navigating your friend who is visiting you around the town. This is because your brain created what's known as a cognitive map, an internal representation of physical space, which can be used to mentally navigate around it. But how exactly does the brain do that? Meet the key player in spatial navigation, the hippocampus. This is truly a remarkable structure, which derives its name from seahorse, buried deep in the brain. For centuries it fascinated researchers, but the exact functions remained unknown. As we will see today and in later videos, hippocampus is essential for a variety of things, such as memory, navigation, and planning. This is going to be an exciting journey. But for now, let's begin with positional system, because this is where it all started. In the 70s, while doing recordings from rats' hippocampus, John O'Keefe and Jonathan Jastrzewski found that there were these special neurons whose activity was strongly correlated with the animal's position in space. Let's do a virtual experiment. We will trace the animal's path as it runs freely around the cage, and at the same time stick an electrode in one of the hippocampal pyramidal neurons, recording its activity. Every time it activates, or in other words generates a spike, which is a fundamental unit of communication between two neurons, we're going to place a dot at the point in space where the rat was located at the time of the spike. You can see what happens. This neuron seems to be a huge fan of this particular patch on the ground. You can clearly see the neuron's preferred location. Due to such spatial specificity, neurons that exhibit this pattern of activity were given the term place cells. And corresponding patch on the ground where the place cell is active is called the place field. Note the distinction. A place cell is the neuron itself. It's a nerve cell sitting inside the hippocampus somewhere, while its place field is the part of the external world. We can't say that a place field of this neuron is the circle 1 meter in diameter in the center of the room. You might ask a reasonable question, but after all, we are three-dimensional creatures. We don't move in a single plane. What about movement up and down? What about fish, birds, and bats? As we know from a few brilliant experiments, place cells are sensible to the third dimension as well. For example, if you wirelessly recorded the hippocampal activity of a freely flying bat, yes, people do that too, you'd see that place fields roughly form spheres in three-dimensional space. And in rats, which moved in a cubic maze that required climbing up and down, place cell activity represented the entire volume. So even the surface-dwelling animals have the circuitry for 3D navigation, which, if you think about it, is not surprising. But what is the role of place cells? Do these neurons really govern the behavior? Are they the working horses of spatial navigation that play an active role in construction of these internal representations of space? Or do they merely correlate with that type of behavior? Let's see how it can be uncovered. The experimental setup is really elegant. Researchers trained the mice to run on a linear track in virtual reality. The mouse was head-fixed and running on a spherical treadmill in front of the surrounding screen. And as it spins the treadmill, the computer-generated picture on the screen updates accordingly, so the animal has a full illusion of actually moving through space. Interestingly, even though it might seem to us, external observers, as just an illusion, there is absolutely no difference from the point of the mouse brain. It receives the matching signals from the eyes, muscles, vestibular apparatus, integrates them together and concludes, hey, I'm moving through space. Consequently, the circuitry employed during navigation in real and virtual spaces should be the same. But what happens to place cells in this case? I mean, technically, the animal is physically fixed in one place, right? Yet, if it can successfully navigate through a virtual maze, there should be some spatially related hippocampal activity that makes it possible by carrying out underlying computations. Indeed, it was observed many times experimentally that place fields do exist in virtual reality, and they tile up the corresponding virtual space. Now, in our setup, as the animal traverses this virtual linear track, we could, by recording hippocampal activity, detect the place cells and their place fields. Then, looking at where the place fields are with respect to the track, we classify neurons according to their preferred location. For example, that this group of cells is active when the mouse is at the beginning of the track. This group activates roughly in the middle, and these neurons fire selectively at the end of the path. In this particular experiment, mice were trained to run to the end of the track and then start licking to get the reward. The question is, what will happen if we stimulate certain place cells, artificially force them to spike when they're not supposed to? That is, when the animal is far away from their place fields. If what we think is true, that the activity of place cells is what drives the spatial behavior, then by applying early stimulation to the neurons that normally fire at the end of the track, we would fool the brain into thinking that it's already there and it's time to start licking. And this is exactly the type of behavior we observe experimentally. Activating specific place cells drives their spatially associated behavior. But what would happen if, on the other hand, we stimulate those place cells that normally fire at the start of the track, somewhere closer to the end? That way, the mouse is quote-unquote convinced that it is located closer to the start than it actually is, and sometimes runs further beyond the boundary of virtual environment, a real-life equivalent of which would be crushing through the wall. And this totally blew my mind when I first heard it. This provides direct evidence of the causal role of hippocampal place cell neurons in constructing the cognitive maps. Now, the question that arises, how does this association between nerve cells in the hippocampus and their preferred patches on the ground take place? It turns out that the layout of place cells is not constant. If you look at the activity of a given neuron, it would have one place field in this environment, different place field in a different environment, and maybe show no activity at all in the third. Such changes in firing activity constitute a remapping of place cell representation of space. It can take a variety of different forms, and the degree of remapping depends on the similarity between two environments. For example, if you repaint the walls and move furniture around, the majority of place fields would change. However, if you hang just a little picture on the wall, only a small fraction of place fields would shift, with the rest remaining mostly intact. Unfortunately, we are still lacking any meaningful way to describe what goes where and according to which rules when remapping takes place. Sometimes, though, the transformation of place fields clearly relates to the transformation of the environment. For example, in the case when a mouse was in a cylindrical chamber with a cue card at a certain position, rotating the card caused the place fields to rotate accordingly, but maintain their relative locations. Even more interesting example was observed by O'Keefe himself, when place fields stretched along with the box, when he varied the aspect ratio of the walls. Hippocampal remapping still remains largely a mysterious phenomenon, but we can at least hypothesize what useful role it might play. What remapping tells us is that different environments have different internal maps. And so, the pattern of place cell activity provides information not only about animals' position within the environment, but also about the identity of the environment itself. So, what aspects of the environment should be altered for remapping to occur? What is enough for the hippocampus to classify two surroundings as different? Interestingly, even the change in non-spatial features can cause a portion of place cells to remap. For example, changing the order in the room, or fear conditioning. If you apply mild electric shock while the mouse is running around in a familiar cage so that it develops the fear of this environment, that causes place cells to remap, even though nothing about the chamber itself has changed. So the internal map of a familiar restaurant you have been going in for years is drastically altered once you have a heart-shattering breakup at one of the tables. We can see how there is this additional layer of information about the context, not just the physical space. And remapping ties this information about physical location in space together with particular events and contexts meaningfully relating to that space. And it raises the question whether place cell is a great term after all. Now we are getting to the limits of this terminology. Yes, initially it was discovered that certain pyramidal neurons in the hippocampus show location specificity. And we still refer to them as place cells in studies on spatial navigation. But as it turns out, they can directly represent non-spatial information as well. Let's consider the following landmark experiment. Rats were trained in a sound manipulation task. They were first presented with the sound of a particular frequency. And to get the reward, the rat had to move the joystick which varied the frequency of a tone produced by a speaker. Basically, they had to make the frequency match the frequency of a sound they heard at the start. As you might have guessed by now, the investigators recorded the activity of pyramidal neurons in the hippocampus, the same type of cell that usually has a specificity to physical location. And here's the kicker. As the animal was varying the frequency, neurons seemed to have a preferred frequency, around which they had high pyrene rates, and showed almost no activity when the sound produced was in a drastically different range of frequencies. They behaved in exactly the same fashion as conventional place cells behave during foraging, having a well-defined place fields. It's as if the rat was mentally navigating in this acoustic space of sounds to find the desired frequency. In that analogy, the activity of a neuron is that of a typical place cell. It's just the space is more abstract. It's not physical location. What it tells us is that place cells can play a more general role. It looks like hippocampus constructs and tracks continuous variables which are relevant to the task. In the case of spatial navigation, such task-related variables would be X and Y position. In the joystick experiment, the most important variable for the brain was sound frequency, and the hippocampus kind of switched modes to keep track of that. Of course, we are still far away from any clear unifying interpretation of what hippocampus does and how it does it. I've already given away the hint that since place cells can encode non-spatial, contextual aspects, they could play a key role in construction of episodic memories. And that is indeed the case, which we will talk about in later videos. We will explore how navigation, memory, and planning beautifully tie together. If you're interested, stay tuned. Until then, if you enjoyed the video, share it with your friends, press the like button, and subscribe to the channel if you haven't already. Goodbye, and thanks for the interest in knowledge.